Cardiac excitability refers to the amount of inward current needed by myocytes, otherwise known as myocardial cells, which are the cells in the muscular middle layer of the heart, to depolarize or generate an action potential. Whether or not it depolarizes depends on if the voltage-gated sodium ion channels are excitable or not. A more excitable cell might have more of its sodium ion channels in the ready state. And even if there was a relatively weak current of ions flowing in, the cell might still easily depolarize. On the other hand, a less excitable cell might have most of its sodium ion channels inactivated, meaning they won't open in response to stimuli. And this is represented by this little ball being stuck in the opening. And maybe only a few of them are actually ready. And so this cell would need a strong current of ions to flow in before it depolarized. Alright, so let's say that this myocyte is from the ventricles. And this is a graph of membrane potential over time. First, a few positive ions like sodium and calcium travel through gap junctions and enter into the cell. And this raises the membrane potential to a threshold level, typically around negative 70 millivolts. At that point, the voltage-gated sodium channels open up, and lots of sodium ions rush into the cell, and this causes depolarization. Right after depolarizing at about plus 20 millivolts, the channels become inactivated, making those channels unavailable for another depolarization. After the upstroke, there's the plateau phase, and then as the cell repolarizes, the sodium channels start to recover, and even though they're closed, they're still excitable. And eventually all the channels recover and the cell repolarizes back to its resting state around negative 90 millivolts. During most of that action potential, the myocyte's unable to depolarize again, and this is called the absolute refractory period. In other words, during the absolute refractory period, pretty much all of the myocyte's sodium channels are inactivated. So even if a bunch of inward current comes from the neighboring cell, it literally cannot depolarize. Now, there are a ton of sodium channels on each myocyte, and each sodium channel operates independently. But overall, most of them stay inactivated after the upstroke, through the plateau phase, and until the cell is repolarized to about negative 50 millivolts, at which point some channels start to recover. And this is the point when the cell would respond to a stimulus. Now, the way that the absolute refractory period is measured is that an electrophysiologist delivers a current to the myocardial cell, and in response it has an action potential. During that action potential, the electrophysiologist delivers multiple bursts of current to the cell at regular intervals. If a burst of current causes nothing to happen, then that means that the cell is still in the absolute refractory period. But if a burst of current causes the cell to depolarize, then that means that the cells come out of the absolute refractory period. Since these bursts were given at regular intervals, we ended up landing just outside the absolute refractory period. It's possible, though, that the burst of current was given at the exact moment that the cell was emerging from its absolute refractory period, but it's probably more likely that the cell emerged from the absolute refractory period before we gave it that burst of current. Also, in some cases, the burst of current that's used isn't very strong, and as a result, the cell might not depolarize even though it's no longer in the absolute refractory period. So all that being said, when electrophysiologists are measuring the absolute refractory period, what they end up actually identifying is called the effective refractory period. Next comes the relative refractory period, which starts at the end of the absolute refractory period and goes until all those sodium channels are recovered. During this period, there's a mix of some of those sodium channels being recovered and available for another depolarization, and some not being ready. But that proportion of ready sodium channels increases over time. Therefore, a cell in the relative refractory period can depolarize, but it needs a bigger stimulus than normal. Finally, we've got the supranormal period, where supra means more than, and this is when the myocyte is more excitable than usual. The supranormal period starts when the membrane potential is negative 70 millivolts, and it keeps going until the membrane is fully repolarized back to negative 90 millivolts. At this point, the sodium ion channels have completely recovered, and the channels are closed but in the ready state again. In this case, it's more excitable because that membrane potential is actually closer to the threshold potential than it is at rest, so it's slightly easier for the cell to depolarize. Alright, as a quick recap, when the cell's at negative 90 millivolts, it's resting, and all the sodium channels are closed but ready to rock. Once a stimulus comes in, the channels open for a short period during the upstroke. The absolute refractory period is when the myocardial cell's sodium channels are inactivated, and it absolutely cannot depolarize in response to a burst of current. The effective refractory period is often used interchangeably with the absolute refractory period, and represents the practical limitations of trying to measure the absolute refractory period and is therefore a tiny bit longer. The relative refractory period is when some of the myocardial cell's sodium channels are open, and so the cell is able to depolarize in response to a larger than normal burst of current. After that comes the supranormal period, which is when the myocyte's sodium channels are all recovered and ready to depolarize. But the cell isn't fully repolarized yet, and is therefore closer to threshold than when it's fully repolarized.